Great welcome to this series on Abaqus. Myself is Jarajan P. This is tutorial number 16 and will provide the capacity analysis of a beam-to-beam fin plate shear connection. So let me first take you to the problem statement. So the Abaqus assembly of the shear connection investigated in this tutorial is shown here. So this is a supported beam. So the supported beam is of size 533 by 210 by 92 UP, and this is our supporting beam, which is of size 610 by 229 by 140 UB, and the two beams are connected through a fin plate of size 160 by 360 by 10 mm thick, and the connection of the supported beam with the fin plate is accomplished through 10 numbers of 120 bolts, and the bolt details are given here. It has got a head diameter of 32 mm and a shank diameter of 20 mm and a shank length of 20 mm again in order to accommodate the web thickness of the beam as well as the thickness of the plate. Now coming to the properties of the structural steel used for the modeling, Young's modulus is 2.1 into 10 raised to 5 MPa, Poisson's ratio is 0.30, and the Fi, the yield stress of the beam material as well as the plate material, will be 275. And as the capacity analysis decide, rather than the engineering stress strain, we have provided the true stress strain data to the Abaqus, and the true stress strain data developed for the steel grade S275 is shown here. And as you can see that the curve that is indicated in blue color, that is the engineering curve, and that indicated in the red color is a true stress strain curve. Now coming to the bolts, we have used class 8.8 bolts with an ultimate tensile strength of 800 MPa with an Fy value of 640. We assumed a process strain of 0.10, the calculations, and the shear loading on the plate is applied through a maximum displacement loading of 15 mm, which is applied at the midspan of the supported beam, and at the midspan we have rather applied a axisymmetry boundary condition. So let us directly uh, see the Abaqus modeling as well as the investigation results. As usual, you have to start with the parts module. So here I'm not going to explain in detail the development of the various parts for this model, and also we will not be discussing in detail the meshing of these parts. I would request all the viewers to see the tutorial numbers 12 and 15 in order to get an in-depth view of how the parts are being modeled and what must be the way in which the partitioning must be done and how the meshing should be done in order to achieve the correct results. So the link for the playlist is already provided at the end of this tutorials. So you can go through tutorials 12 and 15 before getting into this tutorial. So as you can see that yes, we have basically the 1, 2, 3, 4 parts. So this is the main beam, right? And as you can see that yes, the main beam is partitioned across the cross section. If you see the cross section, you can say that yes, it is partitioned across the web as well as across the flange. Now also it is partitioned along its length, and in the middle portion rather we have used a larger density of the mesh because we expect a larger concentration of the stress in this part. So this is regarding the main beam. Now coming to the secondary beam. So this is the secondary beam. So you can say that yes, the secondary beam is a notch, right? So that it can be properly connected with the supporting beam. And you can also see that a set of 10 numbers of 22 diehards are provided in the web of this supported beam. And this hole location should obviously match with the location of the holes provided in the fin plate. Okay, and as you can see that yes, the meshing is the partitioning is done all across the cross section and also along the length. You can see that we have made uh, partitions so that we can provide a larger mesh density in and around the connected part and a little bit loose meshes away from the connected region. So this will improve our efficiency of the computation and also increase the accuracy of the results. So you can see, as you can see that we have also provided some additional circles in order to streamline the meshes, and a proper please ensure that in the connector region near the bolt holes you should do a proper partitioning as shown here, so that you will be able to do a very adequate meshing, and the meshing will have the proper aspect ratio as well as the configuration. So that is regarding the secondary beam. Now coming to the end plate, you can see that this is our end plate. So it is again provided with, you can see that a ton numbers of 22 die halves, and is being properly partitioned. It's a mounting plate. And finally we have got the part, that is the bolt. So you can see that yes, there's a bolt is modeled in a simplified way, incorporating only the head as well as the shank. And remember, shank diameter is 22 mm and its length is also 22 mm. Ensure that it is properly partitioned at the intersection of the head as well as the shank, and also it is a partitioned along its vertical as well as the diametrical axis. So the partitioning is one of the very important thing that one must adhere to see that yes, you are able to do the meshing of the components very effectively. Okay, so this is all regarding the parts. You have seen that there are 4 parts. Because I'm not going to explain all this in detail because it may consume a lot of time, because already tutorials 12 and 15 is available in that playlist. You please go through that. And now coming to the property, obviously we know that we have 2 properties, one for the structural steel that is used for the beams as well as for the fin plate, and the other for the bolt. So let me just show you what are the properties that we have provided. Coming to the steel used for the structural beams and the plate, I can just edit it for you. You can say that yes, we have got a E value of 2.1 into 10 raised 5 and a Poisson's ratio. Okay, here you can give a Poisson's ratio of 0.3. And then coming to the plastic, and as you can see that yes, we have provided the coordinates which consists of the stress as well as the associated plastic strain in the true stress strain format as shown here, because this is very much necessary if we are interested in the capacity and also the connection. So this is all regarding the properties of the structural steel. Now we can go for the bolt also. The bolt is modeled, rather than a material modeling is done in a simplified way. If I edit it, you can see that yes, it consists of again we got a Young's modulus of 2.1 to 10 raised to 5, Poisson's ratio of 0.3. Then coming to the plastic, we have entered only 2 points, one corresponding to the yield stress of 640 MPa and the associated plastic strain being 0, and the ultimate tensile strength of 800 MPa level. It is assumed that the plastic strain will be of the order of say 0.1, that is a 10%. So this is okay for us as far as the properties are concerned. Now the next one will be obviously the assembly, and please refer to tutorials 12 and 15. It tells you how the various constraints like the face-to-face constraints and the coaxial constraints are to be applied. And the final, only the final model is shown over here. You can say that this is your supporting beam, and this is your supported beam, and this is the fin plate, right, along with the bolts. So if you want, I can just zoom it a little bit. So you can say that yes, this is assembly. If you want to see the other sides, you can see that okay, the side. And on the other side, obviously we don't have a plate. We have got only the bolt head over here. So as shown here. So this is all regarding what we call as the assembly. Now after the assembly, you can straightaway go to the step. I can explain you what the steps we have provided. So obviously we have got an additional step known as a step displacement which I have created. And if you want to see the properties, I can just edit it for you. You can say that the displacement loading is applied for a time period of 1 second. And obviously this kind of a problems will require an automatic stabilization procedure which is shown over here. And ensure that NLA geometry label is kept as on. And coming to the incrementation, maximum number of increments are set over here with an initial increment of 0.01, minimum of 1 into 10 raised to minus 15, and a maximum of 0.05. And in the other, we have set the unsymmetry as the matrix storage option. So this means that the step module is complete. Now coming to the interaction, here as discussed in the other modules, we have used the so-called automatic what we call as a surface pair detection method available in Abaqus. So as you can see over here, we have got a total of 41 interacting elements, and here we have provided the interaction property as well. And if you want to see the interaction property, you can say that I can just edit it for you. Here you can say that obviously there's a as far as the tangential property is concerned, we have got a penalty function with a friction coefficient of 0.30, and the normal we have got a hard contact behavior. Okay, this is the interaction property, and now this is all regarding the uh, modeling of the interactions. Now remember here that we have generated four three reference points: RP1 here, RP2, and RP3. RP3 at this point, and these reference points are generated uh, so that whatever loads are to be applied at these ends, it can be applied through these reference points. And remember that these reference points, RP1 to RP3, it is connected to the respective cross sections through the coupling command. So if you see the constraints, that is very clear to you in the material database. If you see here in the model database, you can see that yes, there's a constraint RP1. If you click it, yes, you can see that this RP1 and there's a constraint RP2 and a constraint RP3. Now, one more thing I want to tell is if you see the plate, okay, if you see this fin plate, okay, we did not model explicitly the weld connection, right, between the supporting beam and the fin plate. Instead, what we did is that connection between the fin plate and the web of supporting beam, it is mobilized through what we call as a tie constraint option. So this is what is shown over here. You can see that yes, this is the tie constraint option. So you can also see how does it look like edit. So here you will find that the master surface and the slave surface are already defined, and these two surfaces are being tied using the tie constraint option, and this eliminates the need for modeling the welds. So I think that that's all regarding the interaction constraints and the reference point definitions. Remember that finding the contact pairs by hand, it takes a lot of time. So I would always recommend to go through or to make use of the automatic contact pair detection mechanism available in Abaqus. Okay, and that's all regarding the interaction. Now coming to the loads, as usual, we know that this will include two options. That is one option being two important input. One is the boundary condition, and the second one is the loading, which can be either through the loads or through the displacement loading. So if you go to the boundary conditions, let me just show you the boundary conditions. For example, the RP1, the boundary condition at this end. Please remember that for this analysis, we have used only 1.2 meter length of the supporting beam because it is assumed that the stresses will not be that much, significant beyond this region. That's assumption. And similarly, the supported beam is also modeled using 1.2 meter length. Now, if you see the boundary conditions here for RP1, you can see that we have a restraint the displacement components U1, U2, U3 at the end RP1, and the rotations are permitted. And same is the story regarding the RP2 also. I can edit it for you. You can see that yes, U1, U2, U3 are restrained and the rotations are allowed. Okay for us. And now coming to the RP3, it is assumed that this section it corresponds to the midspan of this supported beam. Accordingly, we have generated the axis symmetry boundary condition at the point RP3, and I can edit it for you. BC edit. So here you can see that yes, this section it corresponds to the x-axis of symmetry. So we don't want any kind of the displacement in the x direction. So u1 is set to 0, and the associated rotations u2 and u3 also set to equal 0. Now the shear loading is applied through a displacement uh, application. So this is what is implemented over here. I can edit it for you. As you can see that we have applied a displacement loading of 15 mm at this RP3. So let me just zoom it a little bit. Yes, you can see that at RP3 we have applied a displacement loading down, and we have applied a displacement loading of 15 mm, which increases linearly in a triangular fashion as shown here. So that's all regarding the boundary conditions as well as the implementation of the loading through the displacement loading at the midspan. Now, what we have is load is over, and the next one is the meshing. And the meshing also, I don't want to take you through all the procedures and all. It is already well explained in many tutorials, right? You can see the playlist. Okay, so here I don't want to just repeat the procedure because it consumes a lot of time. But in any way, let me just show you the meshes that we have adopted for part by part. So you see the mesh. Okay, now coming to first of all the main beam. So you can see that this is the meshing. As you can see that the mesh density is increased near the connector zone, so that, and we have used a little bit a wider mesh in the other extreme regions because that will save our computation time without any loss of accuracy. This is the main beam. And now coming to the secondary beam. So here again you can say that yes. So please see the the meshes around the opening. You should ensure that they are having a acceptable aspect ratio, which should be checked through what we call as the verify mesh option available in Abaqus. Ensure that meshing is always done in a proper way so that your calculations are faster as well as accurate. So now you'll find that because of an additional circuit that we have used for streamlining the meshes, all the elements are very accurately placed, very nicely placed. We don't have any kind of a problem in the aspect ratios, etc. And rather, we have also not used a very fine mesh, a moderate mesh is used. And on the other side, we have used a little bit a larger mesh because we don't expect much deformations across this portion due to the connection. So that is regarding the secondary beam. And coming to the end plate, here as you can see that here again you'll find that yes, the meshes are all very properly aligned, right? You will find that yes, we have got elements with the proper aspect ratios. And here once again ensure that for such cases we need to always divide the plate thickness into two segments across the thickness, because that will improve the aspect ratio of the elements near this portion. Okay, so you will find that we are having elements with a proper aspect ratio over here, right? So that's all regarding the meshing of the end plate component. Now coming to finally the bolt, you can see that yes, the bolt also, you can say that the meshes are nicely placed without any issue at all. And remember that the arrangement of the meshes appears to be very healthy just because we did a proper partitioning so that Abaqus will be able to assign a very healthy mesh for your component. Okay. So that's all regarding the meshing. Now after the mesh, obviously it's a matter of uh, and here one more thing before going to the job regarding the element type. I just want to show you one element type for only bolt. It is the same for all others. We have used for all the structured components, we have used the standard elements, which is basically is a it's a 3D element, and it's an eight knotted element with a linear geometric order. And we did not use the reduced integration, right? So accordingly it is not C3D 8R, it is only an 8 knotted linear brick, C3D8. So this element is used for all the components. Okay, so now coming to the job, yes, it's just a matter of creating the job and running it. Now I have already run the program for you, so let me just start inspecting the results. So as you can see that yes, we have the various components over here. Okay, so let me just take you through the various components. So first we shall obviously see the main element. That will be better for us. So and just remove this as secondary beam. Also remove it. Okay, so as you can see that yes, so So as expected, we find that yes, the stress distribution is larger near the connected uh, zone. That means in this meshed zone, as you can see that it is larger, and the maximum stress, as you can see that it is gone up to say 415. One Mises equivalent stress has gone up to 415 Newton per meter square. And if you want to see how the stresses varied, you can see that yes, that's how the stress distribution looks over to the members or to the main beam. So as expected, we find that yes, the stresses are getting constrained in this middle thread portion. We don't have much problem. So now let us see the other component. That is, let us investigate the secondary beam. So what we can do is we just remove all these numbers. Okay, so we'll have only the secondary beam. So remove. Okay, so as you can see that yes, so this is the secondary beam, so we can see how the stresses are so you'll find that yes, the stresses, this is how the stress variation looks like. Okay, so we can say that here the stresses have gone to a very large level, that's a 765. That's obviously the 1 Mises stress. So how the stress distribution changes, you can see. And you will find that these are the critical zones where you find that yes, there's a red color here, it is around 575, and you may have some very small regions where there's a larger stress concentration. So you can also see how the stresses vary across the various elements. Okay, fine. So that's all regarding the the behavior of the supported beam. Now let me also take you to the fin plate. So because the fin plate is also a very important component for us. So please remember that the ability of this kind of a fin plate connections obviously depends upon the rotational capability of the fin plate component. I'm not going to discuss much on the rotation capacity, etc. In this tutorial because we are just interested in the capacity calculation only. So I will just remove this, and I will also remove my other components. The components, okay. So you can say that yes, this is your this is plate element. You can say that yes, it has slightly rotated. You will see the rotation also later. So you can see that how the stresses have okay, so you can say that as you see. So let me just increase a little bit the deformation scale. So uniform, so let me just put it as instead of 1, for example 2. So let's just see. So as you can see that when we go through the process of applying larger loads, the fin plate starts rotating, as you can see from this. Yes, you can see that it starts rotating. Okay, it starts rotating. Okay, so and we find that the stress are of the order of 695.5. Now, finally, let us see the capacity calculations. So we can just go to the XY data, ODB field output as usual. So let us see what we call as the reaction force R of 2. That's the reactions at the points 1 and 2. So elements a node. You can select it as node labels. That is RP1, RP2. Okay. So you can just plot it. So you can see that yes. So this is how RP1 changes and RP2 changes. So if I want to limit the capacity to just at the point of yielding somewhere around here, you will find that the capacity of this connection will be 2 into this is 250 kilonewton, right? 0.25 into 10 raised to 6 means it will be 250 kilonewton. So it will be around say 250 into 2, so that's equal to 500 kilonewton, right? And then you will find that yes, after this, so this is the time. This is the time along the x-axis, and this is the y-axis. We have got the shear. There's a reactions. Some of the two reactions we have. So we conclude that the connection has got a capacity of the order of say 2 into 250. That's equal to 500 kilonewton. So that's all regarding this tutorial. So you can expect very interesting tutorials in geotechnical engineering and the structural engineering in the coming weeks.